So welcome all. It's a great pleasure for me to present to you Oscar Civit Flores. He comes from Catalonia, from the Digital Legends and Entertainment, where he has 12 years experience developing the Karisma Engine, or actually the subsystem which is in charge of collision and physics. He also has a PhD from the Universidade Politécnica de Catalunya, which I visited. It's a very nice university. And he is also a professor at the Universidade Pompeu Fabra, also in Catalunya. So it's a great pleasure to welcome you.
Thank you. The same for me. Buenas tardes. So what we'll talk today about is basically how we do physics in games. It's not going to be a talk about physics like serious physics. It's going to be about how we use physics in games to do the kinds of things we need to do. So I'll start with a short introduction. He already presented myself, so that will be fast. Then I will talk about the company, Digital Legends Entertainment. Then we'll have a look about on physics engines, what do they do, how they work on the inside. We'll only overview it. And finally, we'll see which are the current challenges and open problems that we have in physics for games, what we cannot do yet, and what we can do to fix it. And I'll give some takeaways, like if you want to put physics in your games, these are the things that work, these are the things that do not work. It's not going to be very technical, and please stop me whenever you want, ask, feel free to stop me. So that's me, and that's important. I'm not a physicist, she is. So if I say something that is not physically correct, probably it doesn't matter, because in games, we don't need to do like real world physics, we need to do what the player expects to happen in the game. So what is physics? From a computer science engineer point of view, it's like looking at nature. Nature is a very complex thing that looks like assembler or worse, and we try to kind of disassemble, like peek into it. We need to take into account all length and energy scales, from atoms to galaxies. We also need to take into account all kinds of phenomena, like nuclear physics, astronomy, electricity, dynamics, thermodynamics. Basically, everything that happens in nature may be investigated by physics. And the final idea or the final objective is to kind of reverse engineer it and get some math that gives us the same results. And that's exactly what we want in the game. We want some math, some code that reproduces the phenomena we get in the real world inside the game. Of course, we have a lot of constraints, and I think I can say that we will never be able to reproduce reality like 1.1. But okay, anybody got the joke? But we need it, at least we need to pretend to be doing like real physics simulation for a number of aspects of the game. The first one is animation. If we want objects to move as they do in the real world, we have to reproduce the laws of movement, object collisions, etc. To get animations that, if we had to make them by hand, would be very, very difficult. Imagine this deck of cards falling. If an animator had to do this animation by hand, it would take a lot of time. It would be not realistic. It would not conserve energy, etc. So we need it for animation. We also need to use physics, at large for render. Rendering is basically throwing rays into stuff and knowing how light behaves and gets into the eye of the observer. So we need to know about light, the interaction with materials, etc. Now it's very common that games have PBR, physically based rendering, which we do use in the last game. You'll see a video later. It's also useful to use physics for sound. When you drop something on the ground, the atmosphere vibrates, the waves propagate, they get into your ears, and you hear the sound. In a game, when you throw something to the ground, nothing happens. You need to detect that collision, because otherwise, if you don't work to detect that, it's not going to be detected. And when this collision happens, we have to do something, like play a sound. It is possible to generate the sound that objects make when they collide. So we can use physics for sound. And also, maybe the most important thing we need physics for is to just make up stupid plots for sci-fi movies or video games. I don't know if you have played Half-Life 2, or Half-Life 1, sorry, but they talk about something. There is the incident, which basically in an antimatter accelerator, whatever that is, there is an unpredicted resonance and just everything. And lots of aliens from another dimension, start appearing. Obviously because of physics. So now we will concentrate in physics-based animation, which is like the thing I'm most acquainted with and what I've been working for the last years. What we typically do in games is basically classical mechanics. We don't do molecular physics. We don't simulate galaxies. We almost never do thermodynamics or like exotic stuff. We think about things that are, or process things that are at the scale of humans, like that can be measured in meters, basically. And we use it for the simulation or animation of natural stuff such as hair, rigid objects, vehicles, break things, etc. The main two applications of physics are, this is a very important divide. If you want to put physics in your game, you want to say, okay, the game is going to work with physics. Like, I'm going to make a football game, and we need the physics of the ball, we need the ball to collide, we need the ball to behave realistically. The ball is the most important part of a football game. So we need the physics to be right. It cannot crash, it must look okay, etc. That would be gameplay animation based on physics. We can also use it for secondary animation. Secondary animation is something that we only use for eye candy, to make it look right. For example, my clothes are not taking part into my talk. If I do this, nothing essential changes. My clothes moves, I look more realistic, I am real. But the game wouldn't change. So when you see a character with hair, clothes, or a flag undulating in the distance, it's this kind of animation. This is important because the requirements are not the same for one and the other. For example, I'm sure you played some game where I don't like violence, but all games have ragdoll, so when you kill somebody, the ragdoll ends up in a very funny pose or vibrating or doing stupid things. That's okay because the ragdoll is not playing an important part in the game. It's not going to break the game because it's looking stupid. But if in a football game you just kick the ball and the ball goes out of the field and never gets back, the game is over. No. So if you have a bug, if you have a problem with the physics of something that you use for gameplay, you have a very big problem. If you have a bug or a minor inaccuracy, something that only is only static, you can get on and nobody's going to notice. They are going to record the video and upload it to YouTube and have fun at you, but nothing is going to be broken. It's very important that physics for games, and everything for games basically, is robust, efficient, and realistic. Exactly in this order. I mean, if it's not robust, you're not going to put it into the game because your game is going to blow up and people is not going to buy it. If it's not efficient, you will be able to put, I don't know, one hair on the head of the character, but that will look stupid. You need efficiency to be able to simulate all the hair or many of the hair of the character. And realism is our objective, but it's not the main thing we need. We need it to look right and fulfill the other two requirements. So some examples of the kinds of models, the kinds of classical mechanics stuff we end up simulating in games. One would be particle systems, things that are small, collide, etc. The other one would be rigids and articulations for characters, for vehicles. Sorry. The other would be deformable curves and surfaces for cloth, for hair, for example. Even for cars, if you have a very realistic car game, when they crash, you can deform the surfaces and they look as if they actually crashed. We can also simulate solids. Actually, my thesis was about trying to do this in real time, which more or less worked, but it's still not ready for a game. This is Quantum Break, which just appeared. They use solid object simulation, like objects deform and break. This is a scene where there is a very big bridge and a ship crashes into it, and it deforms as if it was metal or concrete or the material that. And this is pre-simulated and played back at runtime. So your Xbox One is not running this simulation. It's only playing back a vertex animation of the simulation that has been previously computed. But at some point, we'll be able to do this in real time, which is good and bad for different reasons. We will be getting there. I think in 5 years, we'll be able to do this in real time. And we can also simulate fluids at a very, very simple level by now, because fluids are way beyond the present possibilities of hardware. They are very complex and very expensive to simulate. This Portal 2, this is a very simple fluid. I'm sure you've seen demos of realistic-looking fluid in real time. But usually it's confined to a very small place because it's very expensive. So I don't think we'll see a game about playing in the water and taking cubes out of it in the near future. But someday we'll get there too. So that finishes the introduction. Now I'm going to talk about the company. You can find this information in the website, well, most of it. But basically, what we do at these lessons are, that's not my sentence, it's high-end mobile games. We try to make PS3 games for mobile platforms. That means that we have to work very hard to get good graphics and good animation into a very constrained device that has a smaller CPU, less memory, etc. The company started around 2001. I got there in 2004, I think. It fluctuated, but now it's around 55 people. And we published around, I was going to put a fraction there because one of the games was canceled, so I was going to put 15.5. I didn't want to get sad. Sometimes games get canceled. You work on them and they say, no, this is not going to work, let's finish it. You delete all the files and cry. And we also did some tech demos for companies that make graphics chips. They called us, well, not me because I'm not into graphics, but people at the company made new demos to showcase this technology. It was cool. Right now we have 2 free-to-play games running. One is, well, you'll see both of them. And the amazing amount of 300,000 people is playing every day. I mean, it's difficult to imagine, but we have logs in the server that show this data, so we have to believe it. We've worked with all these platforms and some other ones that I don't happen to remember. And we work with all these companies. Well, Apple should be here, but we already know. So how do we develop? How do we program? At this lesson, one of the main decisions was we're going to do all the technology ourselves. So we basically don't use Unity or Unreal or any other engine. We use some libraries like OpenGL or OpenAL for sound. But we mostly do everything from scratch and in C++. This is difficult, but it's also good because we have complete freedom. For example, if the iPhone 25 is going to come out tomorrow, if we get one of these things, we can program for that, and the same day, our game can be in the store. If you're using an engine or somebody else's technology, it may not be ready when the hardware comes out. For example, if you use Unity, sometimes you are a little bit behind the new hardware. So if you have a company and you want to sell a game, you depend on somebody else. It's like a risk management factor. But basically, we can make games for things that are not yet available in the market. That's the minus one there. The engine is quite big, and it does almost everything, but not everything. We do the things that we need for the games incrementally. And we have separated engine and gameplay teams. So there is basically 4 or 5 people working in the game. I'm always talking about programming, okay? The art and design teams are completely independent. And then there is around 6, 7 people who work in the engine and work for all the games at the same time. So we're kind of decoupled, but we work in the same game or in the same games in parallel. And we also happen to have a physics system because we like travel and we got it. So this is the logo. If anybody understands the Karisma logo, he's going to get a cookie because I don't. Now, how do we use physics? That is the lessons. This is going to be some videos and examples of things we did. And unfortunately, I think I cannot open them. So, yeah, this is a closed simulation we made for a game, for a football game that was canceled, but at this point it was not yet, so he's happy. And also the hair and everything moves. There's some skinning problems in the hand, but it worked. And this was running for 16 characters. And that's when they told us that the game was canceled. This is the collision skeleton. I wanted to show this one because, for example, to model the collisions of the hair and the body of the character, we basically put some capsules or cylinders. She's really pissed. So this is the first thing we did with physics, that is the lessons. Oops, sorry. Then we kept doing hair simulation, but for a happier game. Which has nothing to do with the other one, but it was really fun. It's a dancing game for Nokia. So this is running in a very, very low power mobile. And you can see that, well, the character moves in a nice way, and the hair is not very complex, but it moves. Has anybody seen this game at any point of their life? Well, it's the only happy game we've made. The other ones are about killing people and nasty things, so I'm sorry. We also did some fighting games, like a game inspired in Bruce Lee with hair physics and stuff. Then we made a game, racing game. Maybe you have played Split Second for the big console or for the iPhone. This was for the iPhone, I think 3S. Yeah, before the iPhone 4. And here, for example, the car collisions are detected by the physics engine. And we had to do something like, we had to work extra because the cars were going really fast. So in order to detect collisions, one problem you can have, for example, is that, imagine I have a ball here, and it goes from one side of the laptop to the other. If I only check if it collides here or here in the next frame, obviously it has passed through the laptop. So we had to detect collisions in continuous time, not only checking that time or that time, but the whole trajectory between 2 steps. Because the cars were running like 400 kilometers per hour, something like that. Yeah, well, this can be skipped. We made a bunch of basically sports games that happen to have a ball, so I know the problem of moving balls in sports games pretty well. And it was really interesting because we had to do things like, okay, I'm playing football, I want to pass the ball to my colleague, but he's moving. So we had to predict where he was going to be and shoot the ball, not as we wanted, but exactly where he was going to be in a few seconds. So we had to make this prediction and fulfill it correctly. And finally, we've made, lately we've specialized in three-person shooter games. The first one we made, well, the most successful one we've made until now is the Respawnables, which please download it and play it. It's free, so you don't have to pay anything. Here there is no physics, but what we do within the physics engine is all the collision and raycast queries on the scene. And the last game we've made, is like the most realistic and also most violent one, is this one. Which is only, I think right now it's only available for iPhone 6 and beyond, but we're porting it to Android, so for some kind of Galaxy, I think for the Galaxy S7 or more or less in that. Yeah, this is using physically based rendering, so we had to code the equation, some simplified form of the equations of light to. So that's basically where we have used physics and collisions in Digital Legends. Now we'll have a very short overview of what does a physics engine in a game do. Everybody here is programming, or I mean, somebody has never programmed at all. You have all programmed, okay. So basically, okay, it's a bit cut. A physics engine is a software library. It has functions, you call them, and it has objects, you use them, and it computes something that usually implements only classical mechanics, and human scale. So we can have things that have masses, positions, geometries, rotations, etc. We can push them or make them collide or apply a force, and we will learn how they move. We can simulate how they move. To do this, we have to discretize objects or assign them a set of numbers that describe their movement. For example, a particle has 3 degrees of freedom, x, y, and zeta, that change in time. So what we're going to do is change these amounts according to the laws of physics in time so that they move in a physically correct way. For that, we need the equations of motion, which in general can be written like this. And this simplifies to mass times acceleration equals force in the simple case of a particle, for example. For more complex objects, like rigid objects, the m, the q, and the f are more complex, but essentially it's the same. It's a second-order differential equation that converts forces into accelerations using an inertia measure that is mass, or a resistance to movement amount that is mass. We also have to take into account constraints. For example, if I have a particle and I throw it in the air, you all know that it's going to describe a parabolic trajectory, but what happens when it hits the ground? If I only use this equation, either I model the force that the ground makes on the particle, or what I can also do is, okay, imagine that the ground is the coordinate y equals 0, so the ground level is y equals 0. I can set up a constraint that says the y coordinate of the particle has to be equal or above 0. We do this for a lot of things. For example, if we have a ragdoll, an articulated character, he has 2 parts, like the arm and the other part of the arm, but they are not free. They cannot move freely. They must be attached by the articulation. The articulation is also one of these constraints. And we will be solving the initial value problem, which means we know the initial conditions, we let pass, which are the positions and velocities, we'll increment time, and we want to know where the object is and which rotation has after a small time step, which is usually the time that it takes for the game to refresh, like 60 times per second, something like that. And it's not exactly physics, because collision detection is basically a geometric problem, but it's often inside the physics engine. So the physics engine has usually a separated part that gives you the collision detection and uses it for physics. Now, the basic features you can expect, like if you buy your first physics engine in the market, at least it should have this, rigid body dynamics. It should automatically simulate gravity, drag, which is friction with the air, that makes things stop. And it must allow you to apply forces and impulses to objects so that they move. It must take into account contacts and joints. Joints are articulations. It also needs to provide you a way to query the engine for intersection, not for physics. So if you stop time and you analyze the geometry of the scene, you want to be able to throw a ray and know where does it hit the scene. Or, for example, if you want to create a new character in the scene and you don't want it to be inside the building or inside this laptop, you probably want to find a place where you can put the character and not be intersecting anything. So you can test it, like put a ball, and if the ball doesn't contain anything, you can create the character there. And usually, using a physics engine, if some of you have done it, I'm quite sure you will agree. The basic functionality is very useful, but it's difficult to make complex things with that. So in order to use physics for higher order or more complex objects such as characters, ragdolls, vehicles, whatever mechanism you can think of, there is usually helper functionality. Now, this is an overview of what does a physics engine during a single time step. Like we advance time from t to t plus delta t. And basically what Havoc does, Havoc is one of the oldest physics engines, is it calculates how objects collide. It applies all the forces you apply to objects. It creates the constraints, which may exist always, like articulations, or maybe need to be created and distracted, like collisions. When a collision disappears, the constraint disappears. It integrates in time. Well, it solves the constraints, so it kind of changes the movement of objects so that they respect the laws of physics and the constraints at the same time, and it integrates them forward in time. So we get a new state, and we can then get out the geometric information and render the new frame with the new positions and orientations of the objects. Now, I'm sure you all know about more than one physics engine. If anybody knows about anything, any physics engine that is not here, they can interrupt me. The main ones, or the ones that are more used, are these ones. Yeah, they are more or less in chronological order too. And the thing is that basically rigid simulation is completely solved. Everybody does it. Everybody expects your new game to have rigid body simulation. There is no excuse for not having like rigid bodies in your game. Hair and cloth are also, well, the Y is yes, the N is no. Hair and cloth are also part of some physics engines, so you can have your characters with nice clothes and beautiful hair, and it's simulated by the engine. You still need to render it, but the engine moves it for you. Otherwise, you will have to do it. There are only a few engines that can simulate deformable solids, like the ones we said before. So imagine, a rubber toy that you want to throw to the ground, and you want it to squash and change shape, not just rotate or translate. You can do that with the two last engines. Fluids are, in a simplified way, possible, but not very practical. And the last column is, for me, it's a very important one. It's whether you have the source code available or not. When you use an engine or a library or whatever you want to use to build your game, it's supposed to save you time. No? I want to do physics in my game. Okay, I can write it on my own. It's going to take a while. It's difficult. I could do it. If I decide to use a commercial or a non-commercial library, it should save me work. And probably the only way to assure that you're not going to lose a lot of time with the library is to have the source code. So if sometimes it doesn't work as you expect, or if it fails, which happens. I mean, you can buy a library and it can have bugs. And if you don't have the code, you're going to be screwed because you have a bug which is not in your code, and you cannot even debug or analyze what's happening. So it's a very serious problem, and we've had this. Sometimes we are forced to use external libraries, like because the publisher asks very persuasively that we do. And when there is a bug, sometimes there is bug, we cannot do anything. In the end, we have to ask for the code and debug it. So if you plan to use the library, please check that the source code is available. So wrapping up this part and going to the last one, there is a lot of benefits of using a ready-made physics engine, like everything is expected to work. Most of them are integrated into Unity and Unreal and into content creation tools. So you get the exporters for free, the interaction with other objects of the game for free. And if you have the source, then it's okay. You use somebody else's work, but if you really need, you can get into it and analyze what's happening and fix it or change it at your convenience. The bad things are that physics engines, basically all of them do the same. So they kind of focus on what the users expect. So in the end, all games have ragdolls, all games have vehicles, all games have a standard functionality, and the physics engines, especially the ones which are commercial, focus on these features. There is not many engines, for example, that try to simulate thermodynamics or particle physics or the movement of light under relativity. Is that useful? For some games, it may be, but it's not going to be done by the engine. The other thing is that when you wrap software with other software, sometimes you don't get all the functionality. So, for example, if you use Unity, you normally don't have all the features of the game, of the physics engine that is inside it. You have to bypass Unity. You can do it, but you have to take it into account. And very important, especially for us, if a new platform appears, you have to wait for the person who wrote, or the company who wrote the engine to port it into the new hardware. Or if you want to write a game for, I don't know, a Casio calculator because you are a freak and you don't have anything better to do, or you are really interested in doing it, you have to, physics is not available for Casio calculators, so you would have to do it on your own. The main limitations of physics engines, of general purpose physics engines, one of them is that you cannot easily predict things. For example, the problem I told you before that I want to kick the ball and make it arrive at my team player. With physics engines, what we have is we have this state, and we can know if I set this velocity and this position, what it's going to be in the next frame. But it's not easy to know how to set these constraints so that it gets to the position I want. That you will need to do that by hand. The other thing is that most of them are not strictly deterministic. So if you run the same simulation in two different machines or recompile your code and something has changed, you may not get exactly the same results. This is very important. For example, I have a friend who did a metagame with Unreal Engine, and it was basically a billiard game. So you wanted to see the trajectory of the balls, like bouncing, before actually shooting the ball. So you would predict the trajectory, but then when you run it, it was almost right, but it was not exactly the same. So sometimes you would miss the shot because the prediction was not exactly the same as the actual animation. And it was because of determinism. So also, if you want to do physics over a network, like I throw a ball and somebody else in another server gets the ball and receives it, that's also very difficult to do, and it's not automatic. And if you want to simulate things that are not classical mechanics, you have to do them on your own. Or the physics engine in a creative way to get there. That's true if you are inside Unity or if you are writing it on your own at all scales or at all contexts. These are actual problems and they need to be solved. So this is like the last part when the universe disappears. Well, the title says beyond mechanics. What else can we simulate in games? Which is physics, and it's also fun to play with, but it's not exactly what physics engines do. This is a game called Pixel Junk Shooter, where you could have water and magma and other kinds of even ice. And you could, basically, matter could change phase. So you could, if you throw water into magma, the result is some steam, which is a gas, and the water turned into, the magma turned into stone. So you had 4 different states of matter that were kind of changing one another depending on some rules. Obviously, this was not real physics. This is a way to fake it, but make it look real. You can also simulate something like thermodynamics. This is a great game that many people hate it, but I really loved it. Have you played Little Inferno? Have you hated Little Inferno? Have you loved Little Inferno? Because lots of people was like, the previous game was really good. We built like towers. Tower of Goo was the previous game from these people, which everybody loved Tower of Goo. This one was about putting things in a fireplace and burning them, which sounds really stupid, but it was really fun. And the simulation was really good also. And things could even explode, so that's why chain reactions. We can also pretend that we are simulating electricity. Nobody is simulating electricity because things go very fast when electrons move. So what we do is basically create a ray texture and pretend it's being simulated. We can also simulate magnetism, like forces between objects, Tesla graph. This is a good example that shows that physics in games not always guarantees that it's going to be fun. Have you played Tesla graph? Anybody has played Tesla graph? Okay, you're this little guy and you have the powers of magnetism, so you can polarize positive or negative things, and they attract. And it's also a platform game, so you need to get to this place to push this button and then get out. But you know the solution, but it's so finicky and so tricky to get the actual physics do what you want to do that it becomes frustrating. Not to me, but to many people. You can also simulate relativity. This is a very fun game called A Slower Speed of Light that tries to slow the speed of light, as the name says. So it's a first-person exploration game where you see things as if you were going at a fraction of the speed of light. Like things bend, colors change. Obviously, you're not going at the speed of light, but in this universe, you are. You can also simulate things like black holes, pretended black holes, etc. And you can also simulate sound, which, am I on time? It's very late. Okay. This is a kind of amazing thing that is not in any game, but I really like it, so I'm going to play it. So this is sound simulation from the actual physics of the object. This is a physics simulation, but at the same time generates automatically the sound. There is no recorded sound at all here. They just analyze how things move and vibrate, the materials, everything, and generate this sound. So I'm going to shut up now. Okay. Yeah. So the other thing is that we're in a game, so we can do whatever we want. We are not constrained by the actual laws of physics. If we want to build a tower of like 3 kilometers high, if we don't follow the laws of physics, the tower is going to fall or the material is going to break. In a game, we can do whatever we want, and as long as the game is fun, it doesn't really matter. So, for example, we are not bound by energy or matter conservation. We can just skip it and everything is going to be fine. It says Hollywood physics because there is a web where there are a lot of examples of physics things that Hollywood does wrong, like movies. It's really fun. We can have infinite forces and masses, which is not very common. We also can have instantaneous communication, like a ray cast can be instantaneously arrive its objective or a ray of light. And we can use what I like to call magic constants from the edge of reality, which are basically things that you can put in the game, or multiply, divide, add, or whatever, that if you don't put them, it doesn't work as you expect. They don't have to they don't need to have any like physical demonstration or basis. They just put that number and it works, so why not? You're going to sell more games. And so we can break the laws, but we have to do it in style. So just don't do it because you don't know how to make it right. If you do it knowingly. Any fan of Judas Priest here? I hope so. Now, this, I think it's the one before the last. Yeah, I'm almost finishing. So the main challenges or the main things that are still not solved for physics in games are, if you want to mix objects with very different masses, like a plane or a tank and a cobblestone, a very small stone, the interaction is not going to work well. Because the way we simulate physics requires that objects are of similar sizes and similar masses. You can have objects around 100 times heavier than other ones, but not 1 million times heavier than other ones. The other real challenge is control. When you let objects move following the laws of physics, they are going to follow the laws of physics. So if you want, for example, to simulate a character that is walking, either you simulate all the detail of my feet touching the ground and being kind of soft, and my skeleton, everything that is inside my body up to a certain precision, or otherwise I can, if you model, for example, a character as a rigid body, the joints are completely rigid, and basically what happens is that if you play a walking animation, the character starts bouncing on the ground because you are supposing that it's rigid. So it's very difficult to control something that is simulated by physics. And it's not always fun to play a game with physics-based animation because basically the player has to drive or steer the physics to accomplish the result. Also, if the AI has to take physics into account, it becomes much more difficult. The other thing is that we cannot simulate what I said before, from atoms to galaxies. We have to choose a spectrum of scales and stick to it. Otherwise, we cannot simulate all the atoms in the universe, or even all the atoms in my fingernail. So we have to be very careful and model the things at the scale we need them. And also there is a lot of problems with floating point precision. Like if things are of different scales, the math starts breaking down. We are also quite constrained for both dynamics and geometric complexity, so you will rarely see objects with a lot of detail being simulated. We try to use the simplest simulation model possible for an object. You can have a very complex visualization mesh, like an object with lots of detail, but when you move it, it's often just a rigid body or an articulated rigid body. We do not model, for example, the soft skin of characters. We may render it. We may render the character with soft articulations, but if you touch here, it's not going to deform. It's going to be rigid. That's because we want to keep the computational cost to a minimum. And with this, I finish. It's like the takeaway. So if you got, if you slipped off or if you were sleeping, wake up and just take a picture and leave. The thing is, in a games company, everybody should be acquainted with the basic laws of mechanics, Newtonian mechanics. Everybody. The artists, the designers, the CEO, and the programmers, of course. Otherwise, they may ask you, or you may ask the game to do things that are basically impossible and very difficult to kind of program. So knowing mechanics is good. Also, what I was saying before, realism is important, but only if it's not stopping you from making a fun game. So do whatever you want, but the game has to be fun. And it's also important, especially in a company, to avoid being broke, which may happen. I mean, if you are very very ambitious and you want to make a real world simulation of every leaf of a tree in an open world game. Okay, fine. You're going to either get broke or be hired by somebody really, really rich. But usually it's not good to have a very big ambition. We must be realistic. That's connected to this. If you want to put physics in your game, I'm sure you have to do projects and stuff. Don't add physics at the last time, like, oh, we're going to add physics and everything is going to be better. And we'll save work. That's a lie. Physics basically changes work for artists. Like if I had to animate, for example, my clothes is moving, the artist would have to do it in the modeling program, work, export it, etc. If not, the programmer will have to deal with that problem, use a physics engine, and simulate the cloth. So actually, you're never going to save work using physics. You're just going to convert one kind of work into another one. And also on the design side, if you use physics for gameplay, you have to plan the gameplay of your game and design the environment so that physics works there. The typical problem of the ball leaving the camp and not appearing anymore in the football game, you can solve it putting like high walls around the camp. So that's a design decision. That's connected with the fact that not everything that could be simulated, I mean, you may have the engine, you may have the CPU power, but maybe there are good reasons to not simulate something. And it's often the case because it complicates, for example, things that are simulated are much more difficult to test. So if you have a very big game that a lot of people is going to test, an open world, etc., you're going to have to pay a lot of money to people or hire them to try the game, to make quality assurance. If your game has lots of physics phenomena that look fine, but they are not essential to the game, you will have to test all of them in all conditions. Like if I can throw a ball into that corner and the ball crosses the wall, that's a bad quality for the game. So even if it's not essential, you will increase the complexity of the game, and typically you do not want that. There are a lot of physics things that nobody has simulated, so don't look at the manual. Well, look at the manual of the physics engine, but try to think outside of that also. I already said that. And if you use an engine, do not expect magic. I also did, as he said, at a master degree, and people expect physics engine to be like the solution to all their problems. And sometimes we are lazy, and we just, if a function has well-named parameters, we just call it and expect everything to work, except when it doesn't. So you are planning a physics feature in your game. As a programmer, read the manual, read examples, and try to determine if it's going to work or if you have to change the approach to make it work. So I'm finished. And if you have any questions, I will be happy to answer them. Thank you. So, questions? Who's making a game with physics? Nobody's making a game with any physics? You all did? Okay. I was not here, so. Huh? But was it using Unity? Did you? Box 3, okay. And did you run in, I mean, did you plan the game to use physics, or the mechanics of the game were related to physics? And did you run into any, like, interesting problem or difficult problem? Like, sorry? Oh. Huh? Yeah. So, for example, did it like crash, or sometimes things were jittering or moving in it? Yeah. Anybody else had problems with physics, or has a very good idea for a physics game that they should go home and write and become rich? No? Okay. So if you don't have any question, we are looking for people. I'm not contracting anybody, and I'm not going to pay anybody's salary. So if you want to apply, or you know somebody who wants to apply, just send an email there and don't ask for me because I'm not the guy. But we're looking for all those positions. And especially, it's very difficult to find people who really know C++, like at a professional level. So if anybody is like really into games and wants to be a good engineer and write code and write engines, C++ is the thing you need to know to work at Digital or at Naughty Dog or at any big company that makes like really meaningful games, maybe not ours. You need to know that. And all the other aspects are also important. So when you finish, you can write and, okay, so if you don't have it, yeah.
Hello.
Hola.
Thank you for coming. My name is João Martins. I would just like to ask about the sound. Did you implement? Yeah. In your engine, you have no sound.
No, we detect the event, we detect the collision, and we know which material our object is made of. So then we just play back a sound that has been pre-recorded. So for example, the footsteps, when you walk on a metal surface, it sounds different as if you walk on sand or wood or whatever. But it's pre-recorded. The nice thing with that was that you do not need to pre-record it. You need to set the material parameters, run a very complex simulation, and then you got the actual sound.
Okay. What I meant was about the sound reaching the player, the audio listener or whatever.
Oh, the sound that the players hear.
That the player hears. If there's any simulation.
We occlude it. For example, if you are outside and you get into a room, the way you hear sound changes. We do that. We modulate sound a little bit to make it. And I'm not sure if we occlude sound. For example, if there is an explosion outside the building and you are inside, you hear it differently as if you were outside because the walls and stuff occluded. I don't think we do that.
Thank you.
Yeah.
Hi, my name is Bruno. My question is, are there many people doing PhDs relating to the games industry nowadays?
A lot. We were late because I was in aerographics, and there is a lot of people doing research, not only doing PhDs, but doing like actually respectable people are not young and they have a research trajectory that do things at least applicable to games, and they talk about games in their presentations, and it's a very meaningful and an important application. So for a lot of years, like the movie industry, for example, was the main client of research in physics simulation and graphics. But now games move so much money that everybody wants to like deal with them. So yeah, I could say one half of research in real-time graphics and physics wants to go into video game.
But they all relate more to computer science than the game industry itself.
Well, it's both things. I mean, you cannot have a game industry without computer science. So yeah, there is lots of people doing. Actually, there is lots of people who want to do games, but first does a PhD and then they go to work for the industry, so for the game industry. And the other way around happens, but not that often. So yeah. Okay, with that.
Any more questions? I have one.
Shoot.
Is there a lot of feedback from the research in the physics of games into real physics?
I don't think so. You mean if anybody uses the physics we use for games for real world stuff?
Yes.
I think there is people, for example, who worked in this and now are working in robotics and things that you can really touch. The other thing is that if you use physics for games, ideally nobody can die because your equations or your code is wrong. So that's good. If you are programming a robot and the robot is strong and can kill somebody, you have to be very careful. So I would never ever recommend anybody to use any of my code for a robot that can kill, because I don't want that responsibility. But yes, some people, for example, doing research in robotics, but only like abstract research, so not actually building the robot, use for science programs and stuff. They use game engines for physics, because the focus in real time is very important. And there is also people modeling like drone movement, like planning movements and stuff, and they simulate the drones using real-time physics. So yeah, there is a little bit of cross-pollination, but mostly it's from research to games and not the other way around. But maybe someday that will change.
So thanks a lot, and
Welcome.
thank you.
Thank you. Time. Apply. So yeah, well, I'll stay around for a while, so anybody has private questions.